let's make this as clear as possible before I. One thing I still do on here is I just start talking about everything, you guys. All right, so micro and macro shock is not covered in the first edition of the book. And so the problem is that's the book that I posted on Canvas. However, if you have a second or third edition, I don't know how many are. There might just be 3 now. It is in there, but again, it's something you can easily Google, and it's something that I think. Look, we've had this. I feel like we've had this theme of a conversation numerous times, and that's okay because I think it's good to have these things. There's lots of stuff that you're going to learn in this class, and you might even, maybe you don't learn it. Maybe you just do some problems, turn it in. You go through the motions, as they say. But there are some things that I think you ultimately you absolutely want to take with you. At least don't forget when you're going out and doing what you're going to be doing once you finish school, because they have direct. They're directly connected to most likely what you're going to be doing. I mean, many of you are going to be. I think most of you will be doing this. Is you'll be in an operating room setting, and you're going to have equipment everywhere and instruments. And one of the things you have to be aware of is the hazards that come with electricity, and some of the things that we do as educated adults to make these hazards less hazardous, like different things. You know, like I mentioned things on Monday, like GFIs, which I believe they talk about in the second edition, at least. I don't know about the first. And, so just be aware of these things. And again, like I've alluded to many times, I don't think you're ever going to be giving someone a shot and saying, oh my God, well, you might laugh and talk about that summer you had to take physics with O'Grady, but I highly doubt you're going to be worried about the speed or the flow rate of, a shot coming out of a syringe. But things I do hope you're cognizant of are the things like these pieces of equipment that can be very dangerous if they're not handled correctly, or what happens if I'm not careful with a catheter, for example. Anyhow, I don't want to get too far off topic, but I hope you'll check into that and all that crap. I know that I probably didn't answer. Well, I guess we did answer your question. We found it now. It's in certain editions of the book, not the first. Does anybody have any other questions about macro or micro shock? I mean, look, I always found it funny. I think it's all, and maybe you think maybe you disagree, and I don't know. We can maybe I can always adjust in the future. There's many things I don't like. You saw this on a few of the homeworks. I'd say talk about laminar flow versus this, or what's the difference between hydrodynamics and hydrostatics. It's one thing for me to define a term, but I mean, look, you guys are educated people. You can look these things up. You can read them in the book. You can give me, your version, or how do you interpret it. I think that's much better of a learning tool than me saying this is the definition and then you trying to memorize it. Again, that's my philosophy. I think it's better for you to, read these and ask questions when appropriate. But, for me to just list a bunch of definitions, I don't know how that's a good use of your time or my time. Now, that doesn't mean we haven't defined things. I mean, we've definitely said this is Ohm's law, or this is this, or this is that. But we can't do that with everything. It's not an efficient use of your time or my time. So anyhow, Does anybody have a question about that or comment? By the way, I got the email this morning from the school that says they're going to send you guys the teaching evaluation. So I would highly encourage that you guys do those, and you can be as brutally honest as you want. You can complain about things if you want. You could say that you like things. I mean, it's very helpful for me, and I know you guys might not want to take the time to do them, but for me, it's helpful. What do I do that you guys appreciate and like versus what do you not like? You know, you can complain like, oh, Grady doesn't post the homework scores and it makes me really mad. I mean, you're allowed, you're allowed to do that. So I would encourage you to do them. The people that make decisions actually take those into consideration. So if there's stuff that you don't like that I'm doing, I'll get to see it. And then I can make changes, and hopefully the students that come next won't be as annoyed as you are. So it's helpful to get, what do we call it? What's the word? It's like you're criticized, but it's in a helpful way, right? So anyhow, if you take the time to do that, I'd appreciate it. What you like, what you don't like, what would you change? And again, I'm not making excuses. It's just there are certain things that we could have done better. It's just with the amount of time we had to prepare for virtual summers. I'm trying the best I can, guys. So, okay, that said, does anybody have any other questions about the homework? Going once? And by the way, the last thing I'll say about macro and micro, a good way to keep it in mind is micro just means small at the heart. Macro means lots of it everywhere. That's how I would describe it in my O'Grady terms. I don't know if that'll pass, if that'll be a question on the test or not, but well, I mean like your boards or whatever the heck they are. All right, and the other thing I wanted to say, you guys cool with taking the test next Wednesday, Thursday, Friday? Does that give you guys enough time? I didn't hear from anybody, so like I said, I'll probably just give you guys the exam Wednesday, and then I'll make it due Friday, whatever. I do have to grade them. All right, and being that I can't say no, I'm teaching a bunch of classes this summer, so I have lots of grading to do this weekend. All right. Great. Well, then let's move on to the exciting worlds of well, we're going to start talking about radiation and the fun things. All right, so our next topic is radiation, and and what's interesting about this word is it has a pretty bad reputation, and not all of it is deserved. So one of the things that I've found, you know, when we teaching this class, and then there's other times where these topics come up in other classes I teach, and I guess it's just whatever the world we grew up in, but the word has such a bad reputation, and it's used in a lot of times incorrectly. What is radiation? Well, if we want to define it properly, it's the following. So what is radiation? So radiation occurs when heat transfer involves what's called electromagnetic waves. So that's you've heard of the word wave before, I'm sure, and you've probably heard of electric and magnetic, but what we have is this thing we're going to talk about called electromagnetic waves. And when we have heat transfer and these guys are involved, that's when what we call radiation occurs. So the big question is, we're sort of defining radiation. And if we want to define it, so we need to do something. So most importantly, this means we need to know what that means. And by the way, it should also, you know, we talked briefly in a few chapters ago about heat transfer. And you guys, I mean, I think most humans understand a little bit of the sort of the layman's idea of it, and you guys probably understand a little more just based on things you've done. Well, maybe you haven't done it in a medical setting, but the example I always use is if I'm cold or a patient's cold, and you put a blanket on them, well, what happens? Does the cold patient turn the blanket cold? No. The warmth from the blanket transfers to the patient to heat them up, right? Or when I put a blanket on my kid at night, that heats them up. So heat can be transferred a few different ways. And so we should make that clear. So let me state this as well. So this means there are three ways heat exchange can occur. So this is sort of going back to some stuff we talked about before. There's this idea of conduction, which I didn't ask you to define at all yet. Maybe I'll do that. The second is what's called convection. And then now the third is this radiation. So you should have an understanding of what conduction is, what convection is, and I guess I should spell that better. I'm doing a terrible job of spelling. You can complain about that on those teacher evaluations. You say, oh, Grady spells things wrong. He's sloppy. And then Dr. McCarthy will yell at me. She'll say, you need to do a better job for our students. I shouldn't say she yelled at me. She wouldn't. So, again, convection and conduction, these are good things. I shouldn't say good things. They're things that you should have a solid understanding of. If we just briefly yap about that for a second, but it's also in your best interest to, Google difference. I mean, I'm sure the first hit will be if you Google conduction and convection, it'll give you two examples that you can relate to. My guess is one of them will be the warm blanket. That's one of the typical examples of describing how heat transfers. So I just lost my whiteboard. What is happening? Is this like, are you guys old enough? I shouldn't say old enough. Are you guys here familiar with the movie Dumb and Dumber? Anybody? Andrew, I see you. You don't know what Dumb and Dumber is. How old are you, Andrew?
I know what it is. I just haven't seen it.
Oh my God! There's a great scene where he said, "Our pets' heads are falling." You got to see the movie. That should be that'll be on the final. Everybody has to watch Dumb and Dumber. Every time my stupid whiteboard disappears on my computer, I want to say my pets' heads are falling off. But then it occurred to me, you guys will have no idea what the heck I'm talking about, and then that will make me mad. All my pop culture references are fading away as I become older and older and older. Anyhow, for the old fun times. All right. There it is. It came back to me. So the way I like to think, I like to think of it as like this. So let's just give you a couple examples. So I like to think of this as when objects touch. It's sort of like the layman's terms, you know, cold patient, warm blanket. But really the more specific, what's really happening is atoms or molecules are colliding. So if you're looking for the layman's term of what conduction is, I would offer that it's take two objects, one at different temperatures or than each other, and they touch. But I guess the more physical way is talking about what's really happening is the whatever makes the material up, the molecules of the materials, you know. We talked about this before. The warmer something is, the faster the molecules are moving. And then, of course, you could think of them as bouncing around, and so we have heat transfer that way. And what's nice about why you might offer, why do we call conduction? Excuse me. Well, I don't know, but the word, you know, I would have to look at the historical context, but the word also, you think about, it also helps us illustrate that how heat transfers is going to be depending on what the materials you have. Some objects like and hold heat better than others. We're well aware of, you know, different materials. What is a good conductor of heat? And so we use the word conductor of heat, but we also have conductor. We talk about that with electricity. Like if you go back to electricity, you guys know that you know, a metal is a better conductor. Like a wire is a much better conductor of electricity than, or current, if we will, than say a rubber bike tire. And so we have these similar themes and these analogies when we're talking about heat moving as well. Okay, so and then let's put the example here. So the warm blanket warms a cold patient. So that's sort of conduction. So what is convection? So convection is when an object is moved to a new location. So a good way to think about convection is you take say you take a cup of, I don't know, coffee that's 110 degrees Fahrenheit. And what happens if you put it in on a desk in a room that's 70 degrees Fahrenheit is does that coffee heat the room up? No, right? What happens is that the temperature of that coffee will slowly decrease until it hits the temperature of its surrounding environment. So if I take a hot coffee from the stove, or if I take, my water or whatever you want to say, and then I move it to a different environment, we call that convection. Another way you could think about this is if you go and take your stove and you turn it on, but don't put a pot there, you have a flame. Well, if you're holding your hand right here, I don't feel any heat. But if I move my hand over the flame, now I feel heat. It's an example of convection. So, does anybody have any questions about that? So a good example of this would be all right. So a good thing, and by the way, you might need to ponder this. You could, a good sort of thought experiment, I think. Yeah, I really have to work on my penmanship. And hopefully you're not annoyed when I say thought experiments, but sort of compare and contrast, because you might say, well, okay, aren't atoms and molecules colliding when I put boiling water on a stove? Or excuse me, when I put water on a stove and turn it on so that it starts to boil. So you might need to think about, are these things actually the same, or are they different? Why are they two different things? Because you might argue, well, isn't me putting a warm blanket on a cold patient, isn't that sort of similar to me taking room temperature water and putting it over an open flame? And again, I think these are things that perhaps you, as a student, are best. That's why I call them thought experiments, because I think these things are better learned by you spending time to think about them. Now, of course, you might say you're crazy, O'Grady. I don't think so at all. Perhaps one of the best examples I've seen of this is how they're all sort of related too. Is if you take, is anybody here familiar with a cast iron skillet? Yeah, maybe not just a typical pot. So I don't know about you guys, but I have a couple cast iron skillets. And the thing that's interesting about them is you can't, when they're hot, touch the handle, right? Because you'll burn the hell out of yourself. So what you have to do is you either have to use a very thick rag or an oven mitt, or sometimes these cast iron skillets come with these like rubber sleeves you put on the handle so that you don't burn yourself. So a good way I would get you to think about conduction versus convection is if I take a cast iron skillet and I fill it up with water, and then I turn that on, it starts, the flame heats up the pot, and then the pot in turn heats up the molecules in the water. And so the water boiling, circulating around and boiling, you know, the hot moving up, hot rises and falls and all that stuff, that's convection. Whereas if you decide to be a knucklehead and grab the handle, that's conduction because you're touching surface. So again, that would be sort of the mental image I would ask you to have. And let me draw that. I think maybe some other experts would say you're crazy. I think this is a fairly good way to think about it. So let's sort of draw a picture. So if I draw my pot, here it is. This is going to be like art class. Here's our handle. This is fun today. And we'll put our little fire underneath. This is a gas stove here. This ain't no electric stove. Ooh, that'd be cool if it's an electric stove, then it's electromagnetic waves radiating underneath. That's radiation. What a time to be alive. I bet you there's a picture of that on the internet somewhere. So these are our flames. So the water boiling, that is convection. And by the way, you've maybe have heard of a convection oven before. There you go. And then if you touch the hot handle, that is conduction. So maybe this is a good picture to have. I guarantee you there's something like this floating around the internet. I'll have to find it for you, just so I don't feel like I'm making this up. I don't believe I am. I think this is pretty sound physics, at least at this level. Okay, sweet. All right, does anybody have any questions about this? Are we still here? Is everybody asleep? I definitely see Andrew's alive. That's good. There's at least one of you is alive. There's only 7 of you joining the party today. We have lost many souls as the semester goes on. Alex is thumbing it up. They got to have a better emoji than that. All right, I just kid. You guys all don't have to imagine you're there. Do any of your other classes, do they make you show your face? I feel like that's not fair. Like maybe you don't want me to see where the hell you're at, right? Yeah, I don't know. I don't need to be up in your lives. Or I guess you can have like a background. See, you guys are different. The undergrads are wild. They'll come in with like some crazy ass like Zoom backgrounds, like the Tiger King or some things that are inappropriate, and then I have to decide whether I yell or not. Do you believe in the fall they want me to take attendance in these classes? I said, how is that? You guys are paying adults, and I have to claim you're here and on. I don't think they care whether you're actually, no one's going to yell at you guys. I think they're worried about tracing the Roni if someone becomes infected. Contact tracing, friends. All right, anyhow, let's get out of this picture. This is, that's our picture. So what do we want to do now? So, and by the way, the physics of convection and conduction we've already done because we talked about these ideas. Maybe not in the specific setting of that, but we talked about those ideas from physics. Or from physics, that's funny. But we talked about those things before in previous chapters. Maybe not in these particular settings, but the ideas apply to these. Okay, so we have to go full circle. What is an electromagnetic wave? So that's where we're at now. Okay, so by the way, in order to not drive ourselves nuts and have to write it out all the time, from here on out, we will call these EM waves. So it turns out you're actually familiar, at least with words of these things. Much of what makes your lives in 2020, much of what, I shouldn't say makes them better, but much of what allows us to have, like, for example, awesome technology like cell phones and Wi-Fi, amongst other things, is the understanding that electromagnetic waves exist. Because electromagnetic waves are things like radio waves, microwaves, light waves, X-rays, which, and we could go on and on and on. So what are they? We just gave you some examples, but what are they? How do we define them? So perhaps the best way to state what they are is they occur when charged particles accelerate. So another way of saying that is they are emitted when charged particles accelerate. So if charged particles accelerate, these things occur, they are emitted, they're called electromagnetic waves. So what do they look like? Well, we know they're waves, and anything that is a sort of wave, we have to visualize. We don't have to, but the way you visualize it is through what we call a sine wave. So here's what they look like. It's kind of hard to draw these. So to be more specific, EM waves are synchronized oscillations of electric and magnetic fields. So we draw them like this. So, and this is very difficult to, you're going to have to use your sort of an imagination here. So it is my, I'm assuming that most of you have never had Calc 3, but that might be a bad assumption. So in Calc 3, we learn how to sort of take some of the math we learned in like high school and, and maybe some college. And specifically, we learn how to graph curves. And the curves we graphed in like high school and up through calculus 1 and 2 were of one variable, and they're just a curve in the plane. But as you guys know, we don't live in a flat world. We live in a three-dimensional world. We live in space, three-dimensional space. And so what we want to do is we sort of want to be able to visualize three-dimensional space, and that's really hard to do. One way we try to do it is we try to draw a coordinate system and what I'm going to try to do is I'm trying to visualize that I'm in three-dimensional world. And so what we typically do is we give these guys names. We'll say this is the z-axis. We'll call this the x-axis. And we'll call this the y-axis. So the best way I can get you to think about this is look, you're in a room right now, I'm assuming. Go look at one of the corners. Stare at a corner of the room and think of the corner that goes from the floor up. Think of that as your z-axis. And then think of the intersection of the wall, one wall with the floor is your x-axis, and then think of the other wall with the floor as the y-axis. So another thing that's worth remembering is if I just draw my x-y axis like you guys did many times in school, when you were in school, you had to graph functions. You might remember that there's these functions called the sine and the cosine, and for example, the sine looks like this. Comes up, comes down, looks like that. So this is a sine wave. And you might remember it has sort of the equation y equals, you know, it's going to look scary, something times the sine of something x. Now again, you might not remember any of that. That's okay. Don't get all worked up. Don't say, oh my God, I forget 11th grade trigonometry or something. Let me share something with you real quick that could be useful though. Remember, I showed you this website before, so if I share this, new share. So if I go to Desmos, you can just type in y equals sine of x, and you get this sine wave. And perhaps you guys, you know, I know you guys would have learned this a long time ago. Maybe some of you remember it, some of you don't. That's okay. And then what happens is if I multiply it by numbers, like say 2 sine, and then I put something inside, what that does is that sort of changes its shape a little bit. It's just, and we're going to talk about some of these terms in a second. Perhaps you remember words like period and frequency and amplitude. I don't know if you remember any of these things, but those were things you might have learned about in a trigonometry class, or you know, some sort of high school math class, or maybe you took math in college and studied this stuff. I don't know. But anyhow, you could check this stuff out and play around with it to get an idea of what's happening. So what's interesting is we're going to visualize our electric field and our magnetic field as sort of these sine curves. So, for example, I'll take this blue, and I'm going to imagine that I have, so again, here's what I need you to visualize. I need you to look at the corner of the room, and if right now I'm staring at a wall, and then to the right I have a corner, and I want you to think of this XYZ axis is the corner to your right in front of you. Hopefully you're in a room like this. Man, it sucks not being in the classroom right now. I'd be drawing all over the walls. It'd be so perfect. We'd have so much fun, and we're missing out on all of it. And so I want you to imagine that what I'm going to draw, this blue sine wave, imagine me drawing it on the wall to the right of me. So it's going to come up, and then it's going to go down, and then it's going to go down through the y-axis and then back up like this. So this curve is on the wall. It's laying flat on the wall. And now I'm going to take the red guy, and the red guy is going to look, this guy is on the floor. Imagine this guy is laying on the floor. And so the way to think about this is this blue wave is perpendicular to the red wave. So we can draw some arrows to try to emphasize this. So really difficult to do this. So this is going up, and this is going down, and this is going up. So the blue wave is perpendicular. So one represents the electricity, the electric field, the other represents the magnetic field. So again, the last thing I'm going to say about this, because you really got to have an imagination. That blue wave I drew would be on the wall to the right of me. It would go up, and then it would go down through the floor and then back up, but it's just like I could draw it on the wall. The red guy would be drawn on the floor, and then it would come out of the wall, it'd go back into the wall, into my laundry room, and then back out to where I'm at now. So again, it's quite an imagination you have to have. If you go to, let's see something. I bet you, let's go to the Google machine. So if I Google image electromagnetic waves, yeah, here we go. So let me share this with you in case you're so inclined. I don't know that you are. We'll pretend. So if hopefully right now you're seeing a couple different pictures that I am trying to recreate. Like here's one. Here's one. Notice how one's in the floor, the other's on the wall is a good way to think about it. Oh, here's a picture similar to what I was trying to draw. Does anybody have any questions about this? This is fun, isn't it? Okay, so questions, comments? All right, so here we go. We're gonna we want to study the properties of these waves, and so let's do that. So what's the general form of a sine wave? So what we're going to write might seem a little scary. But again, sometimes we have to deal with things that we don't want to deal with. Okay, so let's just draw a wave without much. We'll start sort of babyish. And so you have to imagine that this thing it has some symmetry to it. So for example, the distance from this like bottom to this bottom is called the wavelength. We typically denote the wavelength with this Greek letter. Lambda. Now, if we add our axis to this, again, you have to imagine that this is nice and symmetric. So the distance this distance, which is the same as this distance, even though it might not look like it the way I've drawn it, but it is. That distance and that distance. So each arrow has length A, and that's the amplitude. So they're all the same height. Does anybody have a question about this? So it's actually pretty interesting. We're using sine waves right now to sort of try to model waves, things that move in waves, like sound waves and microwaves, radio waves. But really, anything that oscillates, like the movement of a pendulum, or anything that like shocks or a spring going up and down, anything that oscillates can also be modeled using sines and cosines. And it's quite a fascinating thing. So, you know, one of the sad things is many students go in high school, you learn some trigonometry, and then you just think it's a big pain. You don't really see why it's important, but it turns out that it's actually very important, especially when we get higher up in math and physics and engineering. Of course, you guys are like, I don't care about any of that. Okay, so all right, any questions? So some terminology that is useful. The period of a wave is the time required to repeat. So we denote this by T. So for example, if we just take the basic sine, so the period of y equals, say, sine of, let's use t, little t, this is 2 pi. Because it takes 2 pi. If you went to Desmos and graphed it, you would see it repeats every 2 pi. Okay, so if we wanted to know how many oscillations we get a second then, so let's be very clear here. So if we want to know how many cycles we get per second, we can define the frequency. So that's defined as 1 over the period. So the units here are 1 over a second, which is called a hertz. And then lastly, the velocity is v equals our wavelength over period, which of course, if you want, can also be lambda times f, the frequency. And then here, we use meters per second. Okay, so does anybody have a question or a comment or anything fun like that? Going once, going twice. So what is the general sort of equation then? So what's the mathematical description? If I want a wave that has a specific frequency, a specific amplitude, so what we like to do is we like to give it the following. We would say y equals a sine of 2 pi times the frequency times the variable. So notice t is the variable. And why are we using t instead of maybe x? Well, we're thinking of t as time. So, you know, your input is time, 1 second, 2 second, whatever. And then this guy right here, if you graph it, whatever f and a are, this will give you the wave of the desired amplitude, the desired frequency, and hence period. Does anybody have a question about this? Comment? Okay. Now, we're not going to get into too much of the weird details of all this because this is left for other courses. Particularly, you have to study more advanced physics and quantum mechanics. And there's this whole idea that things, for example, and maybe you've even had classes where you discuss the basics of this stuff, that, like, for instance, light, I mean, Einstein and some other brilliant people studied this stuff. Light is not a particle, it's not a wave, or it's both, or it's neither. It's very confusing how all this stuff works. And don't forget that what we are doing is we're trying to model what experiment shows us. And so we know that these sine waves can give us good information, but they can only do so much. And when I say we know, I'm not saying necessarily you. I'm saying like the people, the experts, and so we're just trying to relay some of this stuff to, well, not just me, but other people relaying it so that we get a decent idea of what's happening. Okay, so what's important then? We have this understanding that, okay, we have charged particles, they accelerate. Once they accelerate, they emit these things we're calling E&M waves, electromagnetic waves. And the way we try to visualize them is you have two waves perpendicular to each other. One is this magnetic field, the other is this electric field. And so then what we say is, okay, so if these things are happening, there has to be some energy. So we can quantify the energy of the wave or the radiation using the following formula. So Planck's constant is this creature. It's 6.626 times 10 to the negative 34th joules per second. Or you can write this as energy equals Planck's constant times the speed of light over lambda. So there's two ways that we can quantify the energy that occurs with this sort of radiation, or more particularly, we have an electromagnetic wave. Does anybody have a question or a comment? Okay, great. An interesting, and we don't do that in this class because the math's a little more difficult. But if you kind of want to think of a very sort of real world example of what you might calculate with this stuff, you know, many of you have probably been around a light source, and if you get close to the light source, like a lamp or something, it emits. You feel heat, and what's really happening is a light bulb, for example, is going to have an electric and magnetic field around it. And you can actually calculate the energy from these and how intense it is at any given distance using some fancy math. Now, we're not going to do that here, but the reason I mention that is because I would imagine that at one point in your lives, you've been standing next to, or you went to turn off a lamp, and if you touch the bulb, it's hot, right? And so it's not just that there's heat in light, but it's also there's this radiation occurring. So it's something to think about. All right, so moving on. Any questions? What time is it? 10:22. Okay. Going once. Okay, so our next topic is the following. So, what is radioactive decay? It's the next thing we want to talk about. It might be something you know a little bit about. Maybe it's something you know nothing about. Perhaps in school at one point you learned about how we as people date things using what we call carbon-14 dating. So imagine an experiment where you have some sort of, I don't know, anything. You take a bowl and you put some sort of, I don't know, atoms in there. I don't know what it is. And you watch it. And suppose it's something that you watch and every day you take a microscope and look in there and you see that things are disappearing, whatever these things may be. And you realize that there's a specific rate at which these things decay. And so what you'd like to do is you say, okay, we have certain materials or certain substances and we watch its behavior and we notice patterns. And then we realize by doing experiments that we can quantify these patterns and then we can get good information. And what do I mean good information? Well, I guess it depends on what you're doing. But if we're trying to build up if we're trying to build up some sort of theory, and again, let me make this a little more clear. So suppose we're looking at the number of atoms in something, and every day we watch it and we realize there's a pattern that these atoms, say, disappear at a different rate. So one day there's this many, and then the next day we have less. And then the next day we have this many less. And so we recognize a pattern and we start to say, okay, how do we quantify that? So we can model I don't want to say certain things. Let's put it a little more clearly. So this is a very, maybe I shouldn't say disappear. I'm trying to think of a good word. Man, I hate not being in person. I hate it. So, okay, let's maybe start it a slightly different. So this is, let's put it this way. So what is radioactive decay? So this is when a nucleus goes from high energy to low energy. We don't need to know all the specifics. We can get by with just this. So when this happens, of course, energy is released, right? Because we know that energy can never be created. It can never be destroyed. It just has to go somewhere else. And so we can model this and quantify using exponential functions. So what do I mean by that? Well, let's look at some examples. And this goes way back. I think I put one of these on the very first homework and you guys had heart failure, which is fine. We don't get upset about that. So, for example, so suppose we have some experiment or some sort of activity. So suppose we start with, we'll denote it n sub 0 atoms. Then the number of atoms at time t, maybe this is days or months or weeks, who knows? It depends on the constant or the context. I want to use lambda. We used that before. So we call K the decay rate or the growth rate, whatever you want to call it. So K is some number. N sub 0 is some number. Now, it doesn't just have to be atoms. Maybe we want to study something different. Maybe we have a tumor and we're looking at the number of cells in a tumor. Now, where does this equation come from? Well, this is one of the unfortunate things that we have in a class like this, is that no one is expecting you guys to know calculus in this class. Okay, so how does that sort of make, what does that do for us with this particular topic? Well, you need calculus to derive where this equation comes from, and from the basic physical principles. It's not terribly difficult, but it is something that requires some higher math than we are expecting you to have. So one of the unfortunate things is we just say, here's an equation and here's what it can do. So again, let me repeat this because maybe I'm not being clear. I don't know. You know, let's take some sort of, I don't know. What's the example? The book probably uses some. What's a good sort of? Okay, so let's take something that maybe it's obvious to you. Maybe say we take something like plutonium. I don't know. Plutonium sounds like fun. And you put some plutonium atoms in a test tube, and what you happens to notice is that they decay with time. They go away. They disappear, if you will. And if you record how many are decaying, how the rate at which it decays, and you do a little math, you arrive at this equation being a good predictor, this equation being a good indicator of how the decay occurs. And it's not just, you don't have to just do it with atoms, you could do it with cells. You can use, if you want to look at different things like how active is a material, these equations work as well. And in fact, if these exponential functions aren't, if you see that negative number up in the exponent, if that's positive, what you have is you have growth instead of decay, and those types of functions are used for lots of things, one of which is trying to model, say, interest in bank accounts. Anyhow, I mean, we don't want to get into all that. What we need to do is realize it's 10:30, and it's probably a good time to stop and then give you some problems to work on. And then, of course, if you have any questions, you can ask. Does anybody have any questions, comments? So I know this kind of this math right here looks sort of ugly, and it is. It's scary looking, but it's something. I mean, these types of problems, at least that we'll give you in here, they're not terribly difficult. They're mostly plug and chug. It's just, do you know how to use these things? So a good thing you might want to do if you're want to learn a little more about this is you can always Google exponential growth and decay. But anyhow, we'll give you some problems, and if you have questions about them, hopefully you'll ask, and then we'll have a decent understanding of this. So another good thing that I'll say, and I'll leave it at that, is, you might say that we kind of just went from one topic. We're talking about this energy and all these electromagnetic waves, and we're talking about radiation, and then all of a sudden we just jump to our next topic is radioactive decay. So what's important though is, why are they connected? That's another thing you should think about. And is it just some completely a jump from one thing that's completely different than the previous, or is it not? And think about the context of things like energy. Is it created? Is it destroyed? Well, we know it's not. We know it's the law of conservation of energy, which we talked about weeks ago, states that energy just changes. So what does that mean from us going from radiation to radioactive decay? Maybe there's a little bit of details that you might have to fill in on your own, or sort of missing pieces of the puzzle. But hopefully the homework problems will help fill those voids. So, and then if they don't, I hope that you ask. All right, well, listen, I'm going to let you guys go. I thank you very much for joining the party. I hope that we learned something and it wasn't too terribly difficult. So take care. Have a good weekend. Thank you. And I hope to see you guys or talk to you Monday. All right, guys. Thank you.
Thank you.